Okay, good morning, everyone. So it's 10:30. We're going to begin the artificial intelligence session. I'd like to thank everyone for being here today. This new kind of disruptive technology has been changing the industry, and I think it's important for us in a conference like the Leman Swine conference to try to approach this new technology. This has been changing the industry a lot, and it will continue to change it even more. So I'm happy to have three presenters today. They're going to be talking about uses of artificial intelligence and machine learning applied to swine and also to other food animals. So thank you, everyone. I genuinely appreciate everyone. Thank you for the presenters that kindly accepted being here today. With that, I'm going to begin inviting Isabella Condotta from the University of Illinois, Urbana-Champaign, to do her presentation. So Dr. Condotta is an assistant professor in the Department of Animal Sciences at the University of Illinois, Urbana-Champaign. With nearly 14 years of research experience, her work focuses on reducing animal stress, improving animal welfare, and promoting environmental sustainability through the development of precision livestock management systems that help farmers make data-driven management decisions. Thank you so much.
Okay, I'll try to not be behind the computer here too much, but I might need to click. I'll jump right in talking about some opportunities and challenges of AI applications. This AI is artificial intelligence, not insemination, and swine farming. So a little bit of a background. With this world population increase projection of almost 10 billion people by 2050, we'll have an increase in demand for animal products. And on top of that, if we start looking at some labor availability within the livestock sector, you can see that within the past 10 years or so, we've been quite steady on availability for jobs on that area. And when we start looking at hog farms specifically, you can see that the inventory is about steady with the blue bars there, but the number of operations has been decreasing. That, as a consequence, shows that we have more heads per farm to take care of. On the flip side of this, in terms of labor needs to produce 100 pounds of gain, you can see that the labor need is decreasing. That means that we are becoming more efficient in our farms, which is a good thing because we do need to increase efficiency if we want to attend the increase in demand that we just talked about. But we need to do this while still maintaining animal health, improving animal welfare, improving environmental sustainability, helping farmers take care of their animals. We just saw that we have more animals per farm, but still keeping the systems profitable. So one way of addressing these challenges, there are many ways. One way would be using technology in an area that we call precision management of animals or precision livestock farming. The formal definition of this area of research is the management of individual animals by continuous, automated, and real-time monitoring of health, welfare, production, reproduction, and environmental impact. So we are really thinking about gathering data to monitor those animals in real time so we can actually do more informed, better informed decisions about our farms. So how do we do this? We should have information on the microenvironment that the animals are inserted, then collect information on their response to this environment. So environment could be anything from temperature, humidity, to nutrition that you're providing, to the equipment that you're using. And this response could be things such as behavior, activity, weight gain, for example. And this data you can use to develop algorithms that will then provide you with alerts or reports on the state of your farm and your animals. This can be provided to a controller. This controller can be either manual or automated. And based on a desired output, such as feed conversion, for example, you can make decisions to modify this environment or act upon the animals in order to get a different response. This is transformed in feedback for that controller, and this is an iterative system that you can continue improving upon. The area of precision management, you can do research on multiple areas, including the algorithm development, which is kind of where I'm going to focus a little bit because it's an artificial intelligence talk. So when we're developing tools, there is one challenge that we are trying to address, which is how to monitor the animal's condition in a fast, efficient, continuous, and non-invasive way. One solution to that is transform human observation into sensor observation to get more objective measurements and transform those objective measurements into meaningful data. The types of sensors that we can use in the swine industry, generally speaking, they can belong to two categories, such as the non-wearables or wearables. And the non-wearable categories, the cameras have become increasingly more popular. And there are a few different kinds of cameras, such as thermal cameras that can provide you temperature of the environment. They generally are more expensive. RGB cameras, which are depth or 3D cameras that can also provide you with this 3D shape of animals' bodies. And there's your common surveillance camera that can provide you color images, grayscale images, or images during the night, so night vision. For wearables, we have the ear tag. Generally speaking, you can get activity and positioning. There are other sensors that you can put in those ear tags, such as temperature sensor. But overall, you would have an RFID on this tag, and that can be read by an antenna somewhere in the barn. And then the microphone, which can provide you with sound, noise, vocalization. So this is all source of data that we can use to analyze and make management decisions based on that. Just a background on artificial intelligence. So AI is this broad group of techniques that will enable machines to mimic some specific aspects of human intelligence. So just an example, machine vision or computer vision is nothing more than a machine trying to mimic the ability of a human to see, for example. Machine learning, on the other hand, is inserted within this artificial intelligence umbrella, and it's the mathematical operations there behind artificial intelligence. So the goal is to enable computers to learn without being explicitly programmed to do so. And within those models, there is one kind of model that's called the neural network. And when you are working with deep neural networks, or putting in simple terms, when you have multiple levels or layers of mathematical operations within this structure, you call that deep learning. And computer vision, which is kind of the focus that I'll give on this talk, we use deep learning most of the times for this modeling. The difference between machine learning versus traditional program, the traditional modeling, you generally have data and a model, and you feed that to a computer and you get a result based on those two pieces of data. For machine learning, there's an extra step there, which would be this learning step, in which if you're dealing with supervised learning, you would give sample data with expected results to your computer, and then the computer would learn patterns on this data and generate a model. And then this model would be used on a prediction step, the same step that a traditional modeling would use. So just new data along with this model that the computer learned from your sample data is then used for generating a result. Computer vision applications, I brought here a picture of my cat just for exemplifying different applications. Those are not all applications, but some of the applications that have been used in livestock operations. So image classification is the most basic one. You have an image and you get a class for that image. For example, here, cat. Object detection, you add, on top of that class, you add a location for that class with a little rectangle that we call bounding box. So in this case, you have a ball and a cat, and then you also have the location XY position of that box, as well as an output for your model. Segmentation, you go one step further, and you really get the edges or shape of your objects of interest, such as the cat and the ball, and also the couch. There's a few different kinds of segmentations, but I'll not touch into those today. And then you have key point detection, which is as the name says, you have key points within your image. And one application would be to find joints of the animals, for example, while they're walking. One thing that I'll be saying here, IOU, this stands for intersection over union. And it's, as the name says, is the intersection of two boxes divided by the union. This box in black there would be the actual position of my object of interest, and the red box there would be the predicted location of this box by the computer. So the intersection area is the value that you're going to divide by the union of those boxes. So if you have overlapping boxes, completely overlapping, you would have 1 divided by 1, and you have 1 as being your maximum value. But if you have, on the worst case, those boxes not overlapping at all, then you have area of intersection as being 0, so your IOU is 0. So you are looking for the IOU closest to 1. And you probably have seen this confusion matrix here with positives and negatives and true positives and false positives, etc., to calculate precision and recall. But when it comes to detection, just so you understand what that means in terms of bounding boxes. So the ground truth, or the actual box around the ball there, would be this dark blue square. And then if you have a box that's overlapping but less than 50%, then we would consider that a false positive. We are saying that there is a ball in that area when it's actually background. Anything 0.5 and above is considered a true positive in the case of detection. So some examples of use cases that I've been applying in my lab. This is a posture detection. This video is not the best, but I think you can see the yellow box over there around the animals. It's a choppy video just because we collected a low frame rate. But we are classifying those animals into lying and standing and kneeling and sitting position. What we do with this information is calculate then postural time budgets. And for this project specifically, I was working with Dr. Knox at the University of Illinois, and we were looking for prediction of estrus, of gilts in this case. We learned a lot about this project, especially when dealing with gilts. One of the things is just getting ground truth information, a good data source for training our AI models. For example, when do we actually know for sure that an animal is in estrus or not, when we could be dealing with silent estrus? We are using ultrasound as our ground truth, but we had a full group of animals, for example, develop polycystic ovaries, so it was hard to tell when there was a large follicle, for example. But this detection, it speeds up the process of visually having to determine a posture or behavior that an animal is performing. This kind of graph is very common in the AI field. What we have there, and it's possibly hard to read, but I'll explain. On the x-axis, you have the true classes. So for that specific video that I just showed, we had kneeling, lying, sitting, standing, and the background. And then the y-axis, you have the same classes. So what you want to see is, for example, the first class here is kneeling, and we have kneeling up here. So we wanted to see 100% or 1 true kneeling being labeled as kneeling by the computer. So we are really looking for a completely blue, dark blue diagonal and whites around. So this model was performing okay. Pretty good for lying, sitting, and standing. Kneeling position was 0.86 over there. So not too bad, but there's room for improvement, mainly because it was hard to find animals in a kneeling position to train this model. So not enough examples to give to the computer. And here you will see that we have a 0.96 mean average precision at a 50% intersection over union. This just means that if we consider our threshold of intersection over union being 50%, then we get a 0.96 mean average precision. If we want a better threshold, in which location is really important, and we want that box to be above 50, so we average out the average precision across this threshold between 50 and 95 intersection over union, then we are a little bit lower on our precision as expected. Another type of application for detection in computer vision would be for different behaviors. So here we have different classes that we were trying to classify. Oops. At feeder and feeding. At feeder, not feeding, drinking, lying lateral, lying sternal, sitting, and standing. Lots of images were labeled on that and fed into a model. This model was a YOLO model. And this is the resulting video. I need to just... So you see that we're being able to classify those different behaviors. Let me just speed up the video a little bit. There you go. Now we have some different postures. So at feeder not feeding, standing. So this is part of a bigger project in which we were actually trying to look for motherability of the sows. So this is obviously a fairing crate before the sow gave birth. And we are looking for behavioral time budgets and trying to correlate that back with motherability and also number of crushing events. This is just how good we were performing. You can see the mostly dark blue, so doing very good. And here is the mean average precision as the computer trains, meaning the time is passing and the computer is learning more from the data, and our average precision is jumping up close to 1. This is another example of using detection, in this case for nursing behavior, again, from this larger project on maternal ability. We trained models on a Nebraska data set, which is this left video here that I'll just play in a second. And then we were testing how good the model would perform on seeing data in a different location, which is in Illinois here. And our model actually performed very well. And that's due to the fact that we used lots of data to train these models, such as the ones on the left. So, whoop, I don't know what I did here. There you go. So we were looking for a total of 10 classes, 5 different postures, and then either the sow nursing on that posture or not nursing. So we're looking for standing, sitting, lying on the right side or on the left side, and then sternal. So you can see here, sow lying right and nursing, for example. So we had a total of 10 classes. And the other video just to exemplify in a different location. You can see that it's classifying correctly. And again, the dark blues there for all 10 classes, doing pretty good. And the precision recall curve, this area under the precision recall curve would give our average precision. Then we divide this by number of classes to get our mean average precision. Segmentation applications. We can collect segment animal's body to then collect body dimensions, for example. So this is an example of segmenting a top view image, 3D image of a pig. This is the entire pig from the top view, and then we can eliminate some parts like the head and the tail region to create this volume here, this projected volume, which is just the blob of the body without the head. And we can calculate that volume and correlate with different things such as body condition score or body weight. Other dimensions that we can collect using that 3D image would be heights at different locations on the animal body, but also some other dimensions such as widths and lengths. And this is an example of correlation of that body volume that I just showed with body weight. And this is a video of here the animal being segmented, the volume is calculated and then plugged into an equation that we developed. This was back in Nebraska as well. And we are just predicting body weight of the animals, and the RFID system is just kind of giving us the ID. This is the actual top view and color of that system. So the animals are coming to the drinker, and there are some RFID antennas on these panels over there. You can also use segmentation to find some regions of interest. In this case, for example, left and right side of a pig, the head, and then left and right side on the shoulder and the hip of the animal. and then monitor those regions of interest, height in this case, because we had a depth image, over time while they walk. This is an example of an animal walking, non-lame, and then the height over time of the shoulders and the height over time of the hip. You really want to see the pattern of ups and downs. But when the animal was lame, for example, then we have this animal is limping on the top part, and then the region of interest, the height of that region of interest, this is what happens when it's walking. So you can see that the shoulder on this graph on the left is all over the place. The hip is still going up and down, but you can also see the number of steps increasing, and the animal is slower as well. So you can actually use this entire graph as your input to a computer vision model and classify lameness based on that alone, or extract information such as number of steps, speed, etc., and feed that into a machine learning model to classify lameness as well. Another kind of segmentation use. This is for activity level of the piglets. We were looking for the difference in size of the animals plus the activity level for the different buckets of size, and try to, again, this is part of that larger project on motherability. We're trying to see the crushing events correlate with how active the piglets were. This is segmentation applied to posture and behavior. And on top of that, we are also doing tracking, which is segmenting an animal but then monitoring them over time. So you can see there is an ID attached to those animals. So at feeder, at the drinker standing, we were looking for different behaviors of those animals at the nursery phase. We're correlating those with performance. Again, the model does pretty good. And then you can correlate that with different things. For example, feed intake and feed conversion based on how many times the pigs were visiting the drinker or the feeder. Some challenges on this area of research. Working with animals, right? Any living organism can be considered complex, individually different, time variant, dynamic, and that for data systems can be quite challenging. I'll explain why. So this would be an expectation of a pig. If we feed a computer with images that look like this always and say segment the pig, the computer will understand that the pig always looks like this. So when you have something like this happening, the pig just jumping on that scale, then the computer would not necessarily find the pig on the image. This is just a simple example of the types of things we are dealing with. Another challenge is environment. Here we could not put a camera right above the pig, for example, so we had to have this side view, almost kind of on a diagonal view, to find those pigs at the feeder, for example, and we had a number of pigs at the feeder, but if we wanted to do a top view image to calculate body weight, for example, we would have to adapt those models. So we need to consider also the environments that we have available and the farms that they are different as well. Time varying, this is a pig. Over time, we have some AI models to identify pigs, but you can see that in a short span, the pig changes. We have this ear tag specifically making one of the ears floppy. As this pig grows, that ear will go up. They are dirty as well, so these markings here, they are not just markings from the fur of the animal, they are actually dirt. So if we are doing individual identification from images and the pig looks different every day, that's a challenge. Another one that's hard for researchers, measure what's important, don't make important what you can measure. In research, especially with AI, it's always good to collect the more data, the merrier, but it gets to a point that when we think about application, we have to start selecting what actually will make the biggest impact for the least amount of resources. So we really need to grab data, but then focus on that last piece there, which is transform that into information. A quick example of big data that we deal with. So one image has 400,000 numbers, almost 400,000 numbers. If we collect those videos at 30 images per second, we are generating 11 million numbers. And then you can, in 24 hours, you can generate almost 1 trillion numbers. And then maybe you just want one number out of that, which is animal weight, right? So you really need to focus on what kind of information do we need, or even just a final report on that animal weight, and just tell producer, hey, your animals are not gaining as they should. We need to consider customers' actual needs. So this is kind of the final goal here. It's get animal data and transform into information, give advice to producers that will then be transformed into actions, and the outcomes hopefully would be more efficiency, less working time, better work-life balance, and improved health and welfare. That's what I had to say. Those are my students, non-complete list of pictures there, and just some funding sources, and thank you very much.
Thank you so much for your presentation, Isabella. Are there any questions for Isabella from the audience?
With your work on the heat detection, how accurate were you able to get to with the models?
So we were generating this postural time budgets, and we were pretty accurate on determining the time budgets themselves. When it comes to correlating that with the day of our potential ovulation, which is what we were getting with the ultrasound, we got some trends, but the main issue was the number of animals that we had in the end that were usable, which were only 6, so we can't really make any big assumptions statistically. But there was a trend of animals spend more time standing up, getting close to the esters. Yeah, so we're just kind of repeating that with a little bit bigger window. We were looking about 2 days before and 2 days after. We are extending that to around 10 days instead of this 4 days. And just more animals. We had lots of issues with polycystic ovaries, and then just overall just figuring out where to locate cameras and not have a lot of influence from the heat checks from the people on the animal as well. So it's just kind of a lot of learning on that project. But yeah, there were some good trends there. We're just expanding and repeating with more animals.
Any other questions for Dr. Isabella?
How far out do you think this is from a practical perspective of applying it on a farm?
Which of this?
Well, the heat detection one would be a big one.
I mean, there's some commercial products that look specifically for standing versus lying, amount of standing and lying. So it is possible. But when it comes to gilts, which is what we were looking at, we are just trying to figure out if you could generalize the way that you can for sows. So I don't think it's too far off. It's more about repeating this project, but the technology is possible to apply. It's more so figuring out in a way that it's reliable all the time and not just sometimes.
Very interesting talk. Thank you. I was wondering, so a lot of the, I guess, accuracies that you show are being able to correctly classify, activity and posture. So you get that, I guess, activity budget for an individual animal. But the next step of that is to correlate that with performance, or you just mentioned estrus. But for like for a metric of interest to a producer, once you get those activity budgets, how predictive are those activity or posture budgets to, performance metrics of interest to a producer?
So for the nursery project, for example, the number of visits to the feeder, it really gave us a very high correlation, I think above 0.95. With the feed intake of those animals, and then good correlation with then gain. So there is a good correlation. Also, the other thing we're looking for now, next step would be forecasting different things and also comparing so really trying to figure out if we can generalize or if we should be looking at individual level, understanding the baseline of each individual and then forecasting any issues that are off based on what is normal for that specific individual. We hope that you can generalize a little bit, because if you really have to go on an individual level for even how much this animal moves versus now that specific animal is not moving as much, so might be sick. So we are really trying to look for those, but I don't have answers specifically the behavior side, but just for visits to the feeder and correlating with intake, there's a good correlation, and just we can detect activities and the behaviors, but I'm not completely sure yet if we need to do that on an individual level or just a pen level is enough.
This will be the last question.
Have you compared the, you mentioned there are commercial product, so have you compared the performance with your model with the ones that is commercially used? And do you think that
I have not purchased and compared, no, and it's hard to find a report on how really, truly precise those commercial products are. So I would have to purchase and test and compare, but I have not.
Perfect. Thank you so much, Dr. Isabella.
You.